Okay, very good, Bhavika. Okay. Right. So let's go through the example of the solid cone. Okay, so if we have cone like this, whose height parameter is h and base radius is r, okay, then we can understand that the center of mass lies somewhere on the symmetry axis. Okay, so we want to find the position of the center of mass. Okay. This is a volume distribution of mass. So we'll have to take dm as rho dv. Okay. So to understand position of center of mass, or to calculate the position of center of mass, first of all, what we will do is we will take the vertical height as our z-axis. Okay. So here now I will define this as my y-axis. Yes, okay. And wherever the center of mass lies, okay, so I've taken the origin at the vertex, okay, and I've taken the base parallel to the xz plane. So we now have to use this formula. Yes, very good, Kirti. that answer is correct. So here we would get the value of YCM as 3h by 4. Okay. So let's see how that works out. Okay. So what should we take the volume element as? Yes, that's correct.
M divided by pi r square h by 3.
Sorry, m divided by?
Pi r square h by 3.
That is density, yes. Okay. What about the volume element? What type of volume element we should take?
Ring.
Ring or disk?
Disk.
There'll be solid disks, right?
Yeah, that then into area.
Volume will become? So if we take a thin disk over here, it's a disk. So we should take the thickness of the disk as the vertical thickness dy. Okay. And the disk is lying directly at a y coordinate. Y like this, right? So if the radius of the disk is r, this radius is of course capital R. This height is h. So when we express the volume of the disk, it should be area into thickness. Okay. Now can you tell me how we'll relate r with y? Because the variable of integration will be y.
Similarity.
Similarity.
Very good. So you can use similarity of triangles. Very good.
R by y is equal to R capital R by h.
Yes, very good. That's correct. So if you look at this side view, you can see that in the side view, so this is where the disk is lying. So this triangle here can be taken as a similar triangle with this one. So using similar triangles, we have the relation that r by y is equal to capital R by h. So we will use this. Okay. Further, the density here, this would be m upon pi r square h by 3. Okay, so now we are ready to substitute in the integration. So you can see YCM Okay, so 3m upon r square h comes outside. Okay. And then we'll incorporate this. Okay, so if you haven't completed this integration, you can finish this, okay, and show that YCM will come out to be 3h by 4. So that means from the vertex of the cone, the center of mass is at 3/4 the height. Therefore, from the base of the cone, it is at 1/4 of the height. Okay, so on substitution and all, what we'll get here, there's another y inside the integration. Okay. So this establishes Okay, so once again, this is a result to memorize. Okay. So if you haven't done this for homework before, just go through the integration, make sure all the steps are clear. Another thing you can do aside from this is volume of the cone by integration. Okay, so you can do this and you can show that it's 1/3 pi r square h. That is again the way to prove the formula for volume of cone using integration. So that can also be done as a small exercise here. Okay, people, so hope this example is clear. So this would be simply okay. So this would be the general formula of center of mass of a solid cone. Okay. Now the interesting thing here is that the position of the center of mass is independent of the radius of the base. Okay, so that's just an interesting fact to keep in mind that, for example, if we are comparing two cones of same height but different base areas, let's say they are quite drastically different in terms of base area. So you can see the volume of this cone is quite a bit more than the volume of that cone. But still the center of mass would be at the same position. It is independent of the base radius. Okay, now last time did we discuss about the center of mass of a general circular arc which subtends an angle alpha at the center?
Yes, sir, we did that.
Okay, good. So let's look at a quick example, an application question. So this is a quarter disc. So if this point is our origin, we have to locate the center of mass with respect to this. So this is a thin uniform quarter disc. Locate its center of mass with respect to that corner point O. So just try this question out. You can see this is a surface distribution. So you will have to take dm as sigma dA. Right, we had done this question in the last lecture.
Yes, sir.
Okay.
Yes, we done it.
So you have to just take the semi rings, quarter rings, right? So you take the symmetry axis as one of our coordinate axis, let's say, as our x-axis or whatever. So our center of mass will lie on the x-axis. And now we take quarter rings like this. So the quarter ring's center of mass will be somewhere here. So this quarter ring is of radius r and thickness dr. Pi r by 2 dr, that is the area of the quarter ring. So dm is okay. That's dm, and now the x coordinate of this one will be r sine alpha by 2. So that is pi by 4 divided by alpha by 2. So that's pi by 4. So 4r by pi into 1 by root 2 or 2 root 2 r by pi. So now our XCM for the quarter disk, which is for the quarter ring, Km cancels out and left with right. So now let's start looking at questions where we have to do other things, but the position of the center of mass is part of the overall calculation of the question. So in continuation of this, let's look at a simple example where we will use work energy theorem. In addition to that, we will need the position of the center of mass. So our next example, we have a smooth track like this, which ends in a semicircular part like this. Now there is a chain that we are releasing from this position. So there is a thin uniform chain. Its length L is exactly equal to pi r by 2, okay, which is released from the position, released from rest, from the position AB. Find its speed when the chain slips down and is fully horizontal. When the orientation of the chain becomes fully horizontal, at that instant, what will be the speed of the chain? Okay, so for this, it is given to us that this radius is, let's say, 10 meters and G is 10 meters per second square. So we'll just need these two. We will not need the mass of the chain. So it's a smooth track, frictionless. So obviously we can use conservation of energy, conservation of mechanical energy. Loss in gravitational potential energy will be gain in kinetic energy. But in calculation of gravitational potential energy, that is where the concept of center of mass can be used. Yes, people work this out. Anybody got the answer? Okay, so right now the center of mass of the chain will be somewhere here. Okay. And the speed of the chain is 0. So kinetic energy is 0. After some time, the chain reaches here, let's say. This is here, this is here. It is moving with a speed v. And now the center of mass is here. Okay. So if the vertical displacement of the center of mass is h downwards, you can see by using work energy theorem, okay. Okay. Now how we'll find h? So you can see that h is equal to, now this is the bisector line. Okay, so h is equal to now the distance OC will be how much? R sine alpha by 2 divided by alpha by 2. So all you have to do is substitute that here. So this becomes the parametric value, and then you just substitute the numerical things. Yes, Anirudh, your answer is correct. Okay, people, so you'll find plenty of applications of this type where it's useful to remember the formula for the position of center of mass. Otherwise, it will be a very lengthy derivation using integration. Okay, so the question is more about application of work energy, but to be able to find the potential energy difference properly, you have to know the formula for the position of center of mass. Okay, so this formula is also pretty important, the one we have used here, the general formula for position of a circular arc center of mass. We have a thin circular arc which is subtending an angle alpha at the center of curvature O. Okay, then the center of mass lies on the angular bisector at a distance such that OC is given by this formula. So this is a pretty useful formula also. Okay, so that more or less completes center of mass. Yes, by integration applications. Okay, now let's move on to the very last part of the chapter, system of particles, which is application of impulse momentum theorem or Newton's second law, whatever, to variable mass systems. So we can have situations where mass of a system is increasing or mass of a system is decreasing. So there, when we apply Newton's second law, okay, the net external force, which will become rate of change of momentum of the system, net external force equals rate of change of the system's momentum. Now, momentum of a system, you'll remember, was total mass into instantaneous velocity of center of mass. So here m may be variable. Okay, and VCM is also an instantaneous quantity. It's in general variable. So when we look at rate of change of mass into velocity of center of mass, we have to treat it like a product. So differentiation of first term into second term plus first term into differentiation of second, where of course we understand that instantaneous rate of change of velocity is acceleration. So the general equation that we get for a variable mass system is that the net external force equals to the combination of these two terms, instantaneous mass into instantaneous acceleration of center of mass. Or if we write this in impulse form, we can say that it's like this. So this becomes a statement of the impulse momentum theorem or Newton's second law applied to a variable mass system. Okay. So we'll see the applications of this next. Okay, just make a quick note of this. Okay, so let's start with a simple question to begin with the application of this concept. So let's say we have this kind of a situation, a typical type of conveyor belt that you see at industrial level. So this,
So,
yeah,
so rocket is variable mass system.
yes, we'll discuss about rocket. Okay, so we have this industrial type of conveyor belt on which mass is continuously falling. So some particles or some objects are being dropped onto this. So it's being driven at uniform speed. Say 20 centimeters per second. And mass is continuously dropped onto it at a rate of, let's say, 50 kilograms per second. Find the net force applied by its rollers to keep it moving. So very, very simple application of the above concept, because the system is moving at a uniform velocity, but its mass is increasing. So that will make the application of the above formula quite simple. Just work this out quickly. Yes, Kirti and Anirudh, your answer is correct. Okay, so when we apply this equation here, that the net external force is you can see here dm by dt is the rate at which mass is being added. So it is positive. Mass is increasing, so it's positive, okay. And rate of change of velocity is 0 because it's a uniform velocity. So ultimately, when you calculate this, the external force will just come out to be in magnitude this much, okay. So 50 kgs per second into 0.2 will come out to be 10 newtons. Okay, so hope this application is clear, people. Just make a note of this. Okay, now let's look at another example. In this next example, what is happening is that we have, let's say, something like a cannon. This is firing So this cannon is firing shells. At the rate of 10 shells per second. Okay. Mass of each shell let's say half a kilogram, at a speed of v naught equal to 200 meters per second. Okay. At an instant when the cannon's mass, total mass, okay, is this much. Find the reaction force experienced by it from the shells being fired, and find the external force needed to maintain a uniform speed v going forward. So this firing speed v naught is relative to the cannon, okay, not relative to ground, it's relative to the cannon. So from concept of action reaction, you can understand that for every shell fired by the cannon is applying a forward impulse on the shell to launch it. So it experiences an equal and opposite backward reaction impulse. Okay. So because it's firing shells continuously, it experiences these reaction impulses at a continuous rate. So there's a continuous force that is acting on the body of the cannon because of the reaction force coming from the shells it's firing.
So it will be reaction impulse, right?
No, it's force only because see, each shell is experiencing an impulse, but there's a constant rate at which shells are continuously being fired. No?
Okay.
Understanding the point? So a single shell being fired is a single event which will create a reaction impulse. But now per second, there are 10 shells being fired. No? So there's a continuous rate at which impulse is being generated. Understanding?
Yes, sir.
So rate of impulse is force. No?
Yes, sir.
Okay.
Sir.
Yes, tell me, Beta.
When a
Calculated?
shell is fired, the velocity of that cannon will change, right?
So see, that is not important for the first part because we are calculating the instantaneous reaction force. Huh? Okay. And then in the second part, we are applying some external force such that we are maintaining uniform V. No? You understanding? So that reaction force is getting absorbed by some kind of external force. So typically, if the shell, if the cannon is self-driven, like it's a vehicle which has an engine or something, where that external force comes from? It comes from friction generated from the ground.
Yes, sir.
Okay, so let's understand this way, that if you compare the situation, okay, at some time t, let's say the instantaneous mass is m, okay, and this is moving at a velocity v. Now at some time dt later, a certain amount of mass has got ejected out. Okay, and actually in ground frame, this has come out with a velocity v plus v naught. Okay, so this dm mass which has come out, okay, this dm is equal to number of bullets per unit time into mass of each bullet into time dt. It is number of shells per second. Small m is mass of each shell. So you can see that these have experienced an impulse like this, and that is applied an equal and opposite impulse on the cannon. Okay, so the impulse applied by the cannon on this mass is dm v naught, because that is a change in momentum of that dm part. It was moving at a speed v before, now it's moving at a speed v plus v naught. So the momentum of that much mass dm, or that many shells fired in time dt, has increased by dm into v naught. So that is the impulse. So equal and opposite reaction impulse acts on this one also. So force, which we can talk about as reaction force, is rate of impulse. So it is rate at which mass is coming out into v naught. Okay, so this is the reaction force that is experienced by the cannon. Okay, like this, because it is continuously firing shells. So this reaction force just becomes number of shells per unit time. So that was 10 per second into mass of each cell, which was 0.5 kg, into the speed, relative speed at which the shells were fired, which was how much now?
20.
205.
200 meters per second. Okay. So you can see that this reaction force is 1000 newtons.
It will be 1025, 205.
No, the thing is, see, the momentum of the bullets is changing by 200 now. They were initially moving at v, na? They were inside the cannon. Na? So with respect to ground, the initial speed was v, and with respect to ground, the final speed is v plus v naught. So the change in momentum is v naught only, na? Dm into v naught.
Yes, sir.
Okay. Okay. So now if the cannon has to maintain a constant speed, then it has to generate external force through friction on its tires, okay, to absorb that reaction force so that there is no deceleration. Okay. So this is going to be a little bit complicated. So for the cannon, the net force will be F minus reaction force, and that should be equal to rate of change of its momentum. Now this term is 0, but dm by dt for the cannon is minus of n into small m. Okay, so there's an additional term other than the R also. Okay, so understood where this term is coming from now, because the net external force is equal to rate of change of momentum of the system. So if I'm taking the cannon as my system, and on the body of the cannon, there are two types of forces which are acting. The reaction force coming in from the bullets which are being fired forward, and friction generated at the tires. So the net force is the vector sum of these two, which will be like this. Now that will be equal to rate of change of momentum. Okay. So rate of change of momentum will be rate of change of mass into velocity of the center of mass. So rate of change of mass is minus. It's a negative quantity for the cannon. Okay. So m here is the instantaneous mass of the cannon. Okay. And by mass we meant total mass. So which is uniform. Okay. So from this we have the friction generated on the tires is R minus Nm into U or Nm into V, whatever. So you will see that this actually becomes like this when you substitute this value of R here. So it becomes 10 bullets per second into 0.5 into the relative velocity with which the bullets are coming out minus
Sir,
yes.
so on the question, the speed of the bullet, which is, sorry, the speed of the shell is given, is that with respect to the ground?
No, V naught is with respect to relative to the cannon. See here.
Yes, sir. No, yeah, I understood.
Hmm.
Yes, sir.
Just Okay, so now let's move on to the application of this similar type of concept in rocket propulsion. Okay, so what happens is that the rocket engines generate a type of force called thrust, which is like that reaction force that we discussed in the previous question. Okay, so they generate this thrust by ejecting burning gas or exhaust fuel at a very high velocity. Okay. So there are two important things. One is the burn rate. So this is the rate at which fuel is combusted by the rocket engines. So this will be in mass per unit time, kg per second. And the other thing is that this is the relative speed with respect to the rocket at which burning fuel is ejected out. So these two terms determine the amount of thrust, and from that we get the acceleration of the rocket. Okay. So for example, in outer space, zero gravity environment, if at some time t, the mass of the rocket is m and the instantaneous velocity is v, then at a time dt later, the mass of the rocket has become m minus dm and the velocity is increased to v plus dv, because burning fuel of a certain mass dm has been thrown out at a velocity which will become v relative plus v absolute velocity. Okay, because relative to the rocket it is v relative. So the comparison of these two pictures will tell us the rate of acceleration of the rocket. So just make a note up to this first. Okay, so next let's understand how this relation works out. So if we compare the system between these two times, okay, looking at the system at time t over here, and we are comparing to time t plus dt later. So you can see that it's an isolated system. There is no external force because it's in outer space. So the rocket being in outer space in zero gravity environment, the net external force on the system is zero. So there is in fact momentum conservation. Okay. So mv should be equal to the momentum of the rocket. Its mass has reduced, velocity is increased, plus the momentum of the dm mass which is it has ejected. So that's moving in the opposite direction. So its momentum will be negative. This will be the momentum of that ejected mass in the ground frame, or in the absolute frame, you can say, of space. So mv is equal to, now if we open this bracket, okay, so in this expression we can see this term and this term will cancel out, okay, and sorry, this should be minus because it's in the opposite direction now. This is coming out as at a speed v1, let's say, okay. So u relative is equal to, so with sign convention, okay. So substituting that over here, so now this term and this term cancel out. So next step, what this now in this term also, there is the product of two differential quantities, which is negligible. So dm into dv is negligible. So we have m dv is equal to dm into u relative, or we can say m dv by dt is equal to dm by dt into U relative, or instantaneous mass into acceleration of the rocket is equal to the burn rate multiplied by U relative. So this is the equation for rocket propulsion in outer space or zero gravity environment. Now during liftoff, there is additionally gravitational force. It's very easy to incorporate that into this equation. Okay, but the main thing is now based on this quantity U relative into burn rate, that is called the thrust. This is called the thrust generated by the rocket engine. So this becomes that the thrust is equal to instantaneous mass into acceleration, where this is the thrust. So with this, people, we finally come to an end for the concept set of system of particles chapter. So we'll spend 1 or 2 lectures discussing the questions and doubts. Hope you are progressing well with the module exercises also by now, and you would have completed HC Verma mostly. So we have one more lecture this week, I think on Saturday, if I'm not mistaken. So in that we'll discuss doubts and questions from HC Verma as well as your module. Okay. So that's it for today's session, people. Wish you all the best and have a nice day.
Thank you, sir.
Thank you, sir.
Thank you, sir.